Next, I'd like to introduce Eric Pauly, who's going to be presenting DScope, a cloud-native internet telescope. Eric is a PhD candidate at the University of Wisconsin-Madison and is coming to us today from Madison. Welcome.
Thanks so much for the introduction. Like Jason said, my name's Eric, PhD candidate at Wisconsin. I believe I'm one of the 12 students at NANOG this year, which is exciting. I'm happy to be here. Today, I'd like to talk about internet measurement, specifically how shifts in the internet deployment landscape and adversarial behavior frustrate but also enable new internet measurement approaches. Let's start by looking a little bit about what we're trying to measure here. So, if you've ever deployed a service to the internet, you know that services that we deploy on IPv4 addresses are subject to constant scanning and attack. Adversaries scan the entire IPv4 address space every day, ostensibly, though as we'll see, maybe not quite at random. And so, as researchers or as practitioners, really we'd like to understand how adversaries are targeting and exploiting these deployed services. Of course, we're not the adversary. We're often not actually the service that's being deployed. And even if we sit between those two, even if we're the network operator, we often don't have the ability for contractual reasons and so on to actually observe this traffic and analyze it. And so one approach that we use as researchers is that we try to measure by proxy. The idea here is that we'll deploy some vantage point on the network elsewhere in the address space, and we'll measure the way that adversaries interface with, engage with, and exploit this other deployed service. The idea being that if the traffic phenomenon we see on this IP address is similar to that a real service would see, then we've sort of been successful. And so let's look at a few ways that this has been done historically. The first is honeypots. Now I'm sure everyone's heard of honeypots. Oh, it's still up there, good. Honeypots are really sort of older than the internet itself. The idea here is that we're going to pose as a vulnerable service on some other IP address and interact with the adversary. Now this has advantages. We get application layer interactivity, and so we can interact with them and we can cause follow-on behavior, and so we can understand how they're exploiting this service. Downside is we have limited coverage, usually deployed to just a single IP. A natural extension of this is a honeynet, a large-scale network of honeypots. The idea here, of course, is that we simply use multiple honeypot IP addresses. And as a bonus, we can use virtual routing, software-defined networks, and so on to make this a more scalable process. And so now we have interactivity and we have coverage of multiple IP addresses. But if we're deployed to just a small footprint, say a /24, even up to like a /22 and so on, our footprint is still sort of homogeneous. We're getting many copies of the same thing potentially. And what the actual victim is seeing elsewhere in the address space might be different. And so as the internet evolved and we gained the ability to do large-scale data collection, a technique that came out over 20 years ago is large-scale measurement, specifically using internet telescopes. In fact, here in San Diego, we're near one of the birthplaces of the internet telescope at UC San Diego. The idea here is that we'll use large blocks of IP addresses, often that exist for historical purposes, like the 44 dot, and we'll receive traffic here and we'll black hole it, but we'll record what traffic we get. And so we get those 5 flow tuples that we talked about in the last talk. Of course, pro here is that we get these large footprints, an entire /8. But of course, there are some cons. We don't have interactivity, and as I'm sure I don't need to say at NANOG, the capital cost of a /8 that we use just for measurement like this is incredibly high. And so we'd really like something a little bit more efficient. Now, we can sort of look at the space of inbound application layer internet measurement in terms of the coverage, the footprint that we achieve, and the level of interactivity that we have with the adversary. So naturally, the honeypot exists right here. We have application layer interactivity and sort of coverage of a single IP address. The honeynet is a natural extension of this, same interactivity, multiple IPs. And these existing telescopes sort of sit right here. We have no or limited interactivity, but we have a large footprint, multiple networks or a large block of networks. Now these techniques have been incredibly useful for our understanding of adversarial behavior. But as we'll see, there's sort of an increasing utility over sort of both of these dimensions, right? And so even though there's been a lot of benefits to these, they've given us insights on emergent threats, botnets, backscatter, and so on. The real question that arises is, can we achieve high interactivity and a representative footprint, such that what that victim service sees is sort of within what we see? At the same time, the internet deployment and measurement landscape has shifted dramatically in the last 20 years. Public cloud providers, CDNs, and software as a service mean that increasingly many organizations deploy their infrastructure in one of these large providers. Effectively, the service space has been consolidated. And so adversaries can target these valuable IP address ranges. The second is that the semantics of adversarial behavior have moved up the protocol stack. It used to be that a 5-tuple was sufficient to understand what an adversary was doing. Destination port is the application being exploited. But nowadays, many new protocols are actually written on top of things like TLS and HTTP. And so these 5-tuples really don't give us the whole story of adversarial behavior and intent. And at the same time, those adversaries that we're trying to understand and measure have become more sophisticated and distributed. Adversaries can identify where telescopes are and avoid them. And so, in response to this, we need to design a new type of telescope, a telescope designed for the modern reality of internet deployments. To achieve this, we wanted to get representative traffic, the same traffic that cloud-deployed services would see, for instance. We wanted to have interactivity with the adversary on this footprint, both to collect this application layer data and elicit sort of deeper, more sophisticated adversarial behavior. And finally, we wanted to be agile through the IP address space. What this means is that the footprint of the telescope should constantly change so that adversaries cannot identify and avoid it. To achieve these goals, we developed and deployed DScope, a global, dynamic, interactive, cloud-based internet telescope. Now, that's a mouthful, so let's look a little bit more closely at how the architecture of DScope is specifically tuned to achieve these goals. As I noted, we sort of hypothesized that cloud-deployed services would be receiving a new space of traffic phenomenon, that is, attacks that are specifically targeted by adversaries at public clouds. And so we deployed DScope on a major public cloud provider, in this case, Amazon Web Services. We actually did a preliminary analysis of different cloud providers to understand sort of what price performance we could achieve using our architecture, and due to a variety of factors, Amazon is actually sort of price optimal in this space. Within Amazon, we continually spin up virtual machines using EC2. Each of these instances boots up and it accepts traffic on TCP on all ports. And then after 10 minutes, it shuts down and saves all of its data. Keep that number in mind. Now, it actually turns out that, of course, network traffic is just data, and the Linux kernel is extremely good at routing this data. So we do just a little bit of IP tables tricks to make this happen. After instances shut down, we automatically replace them with new instances continually. In this way, because of the way that Amazon allocates IP addresses, that is pseudo-randomly from a shared pool, we continually sample new IP addresses and receive coverage of new phenomena. And DScope is global, deployed in 16 Amazon regions worldwide. In effect, whereas existing darknet and conventional telescopes sit on a homogeneous IP address range, one large /8 for instance, and receive many copies of the same traffic and aren't interactive, DScope sits on a wide variety of IP address ranges in many different networks, or specifically many different IP prefixes, receiving different traffic and interacting to elicit sophisticated behavior. Now, of course, DScope isn't just a data collection platform, but also an analysis platform. We take all of this data collected by these instances, about 30,000 instances a day. We consolidate them into packet captures, information on HTTP requests, associated DNS records, and so on, and we store all of that to S3. And on a daily basis, we produce these archival data files that we can sort of use to look back in time over the years about how this traffic phenomenon changes. We extract flow tuples and so on, and then we merge in a couple of other data sources like ASNs, GeoIP, and so on from those clients. And then we did a lot of analyses of this to try to understand how this vantage point really differs from prior works. Additionally, we're also working to sort of release a lot of these data products, both for researchers and practitioners, to understand how adversaries are targeting networks and how that changes over time. Let's look at DScope by the numbers. We've had DScope deployed on Amazon for over 2 years now, and in that time, we've actually been able to allocate, this is an older number from the submission of this, but over 7 million IP addresses. And those addresses actually spanned 110,000/24 networks, thanks to the large-scale footprint that we achieved by using a public cloud provider. Now, to our knowledge, that's actually more /24 networks than any telescope that's deployed in this way. And as a result of our deployment methodology, the types of source traffic that we see, application layer data that we see is sort of similarly broad. We achieve coverage of millions of source IP addresses. And something that I'm perhaps most interested in is that we achieve relatively good price performance. Whereas the capital costs of large-scale telescope footprints, those millions of IPs of footprints are extremely high, we perform the same measurement with only a few $100s a month paid to Amazon for these IP addresses. And so what we really wanted to understand was how the coverage of traffic phenomenon differs from these cloud-based telescopes versus conventional darknet telescopes. And so we took data from Merritt's Orion telescope, which is deployed on a large footprint of sort of contiguous IP addresses, and we compared who was talking to the cloud versus who's talking to these darknets. And we came to a wide variety of findings about how these two targets differ, as well as how we deploy effective internet telescopes. Today, I want to focus on 4 of these findings that highlight specific ways where cloud internet phenomenon and telescopes differ from conventional approaches. These span the ways that our footprint and interactivity impacts coverage, as well as how we can achieve statistical validity in this sort of cloud sampled data set, and how we achieve that price performance. Let's start with coverage. Now, existing telescopes primarily work under the assumption that internet scanning is random. And so if an adversary is scanning any IP address within the address space, the more IPs we control, the more coverage we get. And historically, this has been shown to be true in some senses. But we hypothesized or we theorized that this might no longer be the case. And so we want to understand if internet scanning is truly random. Now to do this, we did sort of some fun statistics, and we're going to phrase this as a hypothesis test. I'll give you the intuition here. If scanning is random, and adversaries are randomly targeted in the address space, then how many darknet IP addresses are contacted versus how many DScope IP addresses are contacted effectively is a function of the size of the two telescopes, how many addresses they have. And so what we're going to do here is we're going to look at a 2-dimensional histogram of, for each scanning IP, how many telescope IPs it contacts. This region on the right is where we would expect all the traffic to center around if scanning is random. And so we look at a week's worth of data comparing these 2 vantage points, and what we see is indeed, for a lot of traffic, that is the case. There's a massive amount of scanning going on the internet that is just truly random across the IPv4 address space. What's perhaps more interesting, though, especially for this work, is this distribution over here. These are scanners that contact many, many cloud IP addresses, but few, if any, darknet IP addresses. And so it's not random scanning, it's really targeting the specific qualities and the specific footprint of cloud providers. Or it's avoiding those darknet telescopes. And so we see that by deploying our telescope on a public cloud provider and getting off of the darknet ranges, we see a whole class of traffic that is simply invisible to conventional approaches. Additionally, we wanted to understand whether scanning was sort of random but just targeting cloud IP addresses or targeting specific IP address ranges, or if it was sort of sequential through the IP address space in a way that would sort of frustrate our analysis of it. One interesting quality of the Merritt Orion telescope and Amazon Web Services is that Amazon actually recently acquired many IP addresses that used to be part of Orion's telescope. And so, if adversaries are treating the telescope differently, we would expect many of those adversaries to continue treating addresses differently, even though they're now owned by Amazon. We'll actually see a little bit in a couple slides how that plays out in a different setting. But what we did here was we looked at DScope IP addresses that were in the same /8 that was previously part of the darknet telescope. And we looked at whether those showed the same phenomena as other DScope IP addresses. The question here is, are IP addresses near Orion, near the darknet, more likely to be similar to it than, say, any other /8 that Amazon owns? And the reality is that we really saw no difference here. And so what we conclude is that adversaries are really not just avoiding this whole /8 thinking it was previously the telescope, but they're specifically targeting cloud services. So we've seen how moving the footprint of our measurement apparatus to public cloud providers gives us new coverage, but how does that interactivity that we deploy induce adversarial response and give us even more coverage of behavior? Let's look at an example of where this might play out and then see if we can prove that it happens in practice. Imagine that we have a botnet, think say the Mirai botnet, and that botnet is scanning the entire internet at randomly looking for services. It's going to send requests out, and of course some of those requests will hit the darknet, and some of them will hit DScope. In contrast to the darknet, DScope is actually going to reply to these. It'll complete TCP session establishment. At this point, the botnet is going to send information on active services to the adversary via a command and control server. And the adversary is the one that will actually deploy the exploits. They'll attempt to sort of compromise these servers by sending a follow-on scan to discover vulnerabilities. The important thing to note here is that this follow-on scan is the one we're really most interested in. That's what's going to tell us what attacks adversaries are deploying, what services are vulnerable, and so on. And so the question here is, does DScope receive these follow-on scans? Again, we're going to use some cool statistics tricks here and look at a specific distribution over botnets and adversaries. The idea here is that we're continually allocating these new servers. And so what we're going to measure is when adversaries contact the telescope compared to when we start up IP addresses. So recall, we run each IP for 10 minutes, that's 600 seconds. The botnet is scanning the internet randomly. And so effectively, when they talk to the telescope is going to be uniformly distributed over time. That's that blue line there. And this is a cumulative distribution of when they connect. In contrast, the adversary needs to wait for this initial scan, the response from the telescope, and then the message to be sent to the command and control server. And so when the adversary connects to our IP addresses is delayed in time. That's that black series there. And so what we're going to do is for every single scanner that contacts our telescope, we're going to do some statistics here and try to understand whether it follows the blue line or the black line. Of course, there's some complexity here, and we apply what's called a KS test, actually. So we sort of figure out what's the probability that an adversary is the blue line or the black line. And for some of them, the probability is so high that it's the black line that effectively we know with certainty. Things like there's maybe a 1 in 10 million chance that it's the blue line. Of course, in statistics, nothing is ever certain. And so we did this test on the millions of scanners that contacted our telescope, and uh-oh, there are some lines missing there. Okay, what we found was quite interesting. There's a bunch of black lines missing here, but the red line is effectively where they all are. We found a variety of scanners that were delayed in time. They followed where that black line originally in the last slide would be. And so they have to be responsive to service interactivity. They can't simply be scanning the internet at random. And we looked more carefully at how these adversaries behaved, and we actually figured out the information flow between scanners. We were able to identify groups of scanners that were scanning at random, and then we identified command and control servers of botnets that were using this information. And so this shows us that the interactivity of our telescope not only gives us those application layer payloads, but it also elicits follow-on and more sophisticated adversarial behavior. And again, this behavior is invisible to conventional telescopes. So, we've seen two key advantages of deploying our telescope IP addresses on public cloud providers and having interactive collection. And those are that we get improved coverage and we get improved interactivity. But of course, everything comes at a cost. And in the case of cloud IP addresses, it's one of statistical validity. The challenge here is that every single IP address on a public cloud provider is unique. The cloud provider bought it at a different time from a previous provider, and dozens or maybe even hundreds, thousands of services have been deployed on that IP address since it was acquired. And so the way that adversaries target each IP really depends on that rich history, including the types of configurations, think things like DNS records that are associated with the IPs. Let's look at an example. We wanted to understand whether adversaries were targeting specific regions of Amazon Web Services. And so we looked at the distribution for DScope IPs in different regions of how many source IPs were seen. The orange is the US 1 region, specifically US East 1. And the blue one is a region in Europe. As we can see, these two distributions are quite different. And so one might naively think that scanners are really targeting the US 1 region. In reality, the situation is a little more complex than that. In a parallel study, we tried to understand whether the year in which Amazon purchased IP address ranges and started advertising them affected the amount of adversarial scanning of those IP address ranges. And what we found was quite surprising. IPs acquired most recently by Amazon in 2021 actually received substantially less scanning activity than previously or sort of longer owned IPs. These are nice and clean addresses. And so one possible conclusion here is that there are many adversaries out there using outdated lists of cloud IP addresses to target cloud IPs. When we account for this difference in distribution, the differences between regions at an aggregate level actually sort of evaporates. They look very similar in terms of distribution. And so we see that by having this large footprint, a large sampling of cloud IP addresses, not only are we able to eliminate these sorts of confounding factors, but we can identify them and characterize them statistically. Now, one thing I said in the previous slide was that we didn't see a lot of difference between geographic regions. Just as sort of an interesting example, that wasn't exactly true. One thing that we did was looked at the types of protocols that were being exploited against different regions. Here, we have a Hilbert diagram of port 445 traffic seen by Amazon IP addresses in the 3./8. The 3. Was a range that was actually acquired wholesale by Amazon several years back. If we look, actually different subregions of this Hilbert diagram exist in different physical regions of the world. And if we look at Asia-Pacific regions, we actually saw dramatically more targeting of this specific protocol. And so there are sort of some differences in practice, and we're able to identify those using our vantage point. Now, we've seen, of course, the benefits of our footprint and interactivity and the benefits of having many, many IP addresses. But that coverage comes at a cost, specifically that we have to pay Amazon for every IP address that we use on an hourly basis, and it can get quite expensive. And so our goal here is to obtain maximum coverage of phenomenon while paying for the minimum number of IP hours. What this really comes down to is how long we hold IP addresses for. Recall that we held them for 10 minutes. Of course, we could hold addresses for longer, but then we could study fewer IPs. It's a trade-off. And so the question is, how does our coverage vary with how long we hold IPs? Here's the empirical data, up to 600 seconds or 10 minutes. Our coverage of phenomenon increases over time, but if we look at our coverage of phenomenon per hour or per dollar of measurement, we actually reach a plateau. So if we measured for longer, we wouldn't get as efficient of coverage. In fact, we can sort of extrapolate this. We can, again, use statistics, and we can extrapolate this out and see that if we measured for longer than 10 minutes, our yield, our economical yield for the telescope would go down. But additionally, if we measure for just a few hours, we get very high coverage of all the phenomenon that that IP address would see. This is really a stark contrast with a lot of conventional wisdom in the measurement community, where existing telescopes sit on the same addresses for months or years. We can also do things like look at coverage of autonomous systems and really any other phenomenon, although the trend is effectively the same. Short duration measurement yields better coverage per dollar. And so we see that this deployment technique can actually be optimized for these different price goals. And of course, we're optimizing for maximum yield. Now, we've seen a ton of great advantages of cloud-based measurement here, but I think one of my favorite outcomes of this is that we're producing useful data, ideally for the community. And so we're actually publishing a lot of this data as open data that anyone can look at, analyze, and use to yield new insights. A lot of this is actually available already on dscope.org. We're publishing these things in standard formats like PCAPs and so on, and we have 2 years of data already. In some cases, when the data is potentially sensitive, things like application layer payloads, we need to do some data agreements for that, but those are a work in progress. Definitely reach out if you're interested. We also have a bunch of interactive visualizations online about how new threats are being exploited on cloud services and also how we deploy services on the cloud. Let's look at a couple examples of how this data is useful. So we get, from this telescope, we get broad application layer traffic targeting cloud IP addresses. We get some specific phenomena on cloud services, and we get sort of this general purpose telescope data. Think 5 flow tuples. First, let's look at application layer data, vulnerabilities. One thing that we can do with all this application layer data, terabytes of it, is that we can match it using IDS rules to understand vulnerabilities, CVEs, and know when they're being exploited in practice. And we can look at where those exploits are coming from too, to build block lists automatically. One thing that we found, which is quite interesting, is that the specific vulnerabilities being exploited on cloud services tend to be far more severe than those in general. So the blue here is the distribution of sort of all the vulnerabilities from the last 10 years. The green is the list of known exploited vulnerabilities from CISA, and the orange is sort of what we've collected. And we see that the impact factor on these really skews high. It kind of makes sense because they're network exploitable. Additionally, we also compared when DScope sees exploitation compared to existing state-of-the-art. One thing we did was we looked at CISA's list of known exploited vulnerabilities, and we found that by deploying on clouds, we actually see evidence of exploitation before this amalgamation of all of these different sources by the US government. And so that's really an interesting data set. We're in the process of reaching out to CISA to sort of incorporate these results into the KEV automatically. One example of this is sort of really the notable log4shell. Right, so log4shell, if you're not aware, you probably are, was an exploit against the log4j logging library, which was in use by literally millions of pieces of software. And what we found was, by being deployed on public cloud IPs, we saw some of the first evidence globally of exploitation of this vulnerability. Indeed, if we took the signatures from the data that we collected and tried to generate block list rules on the fly, I have some evidence that we could actually prevent a lot of exploitation of emergent threats like log4j in an automatic fashion. Another example that we measured was the ability of adversaries to exploit previous tenants, previous owners or controllers of IP addresses. The idea here is that when a given tenant of the cloud allocates IP addresses, they associate configuration with it. This could be anything from DNS records to a sticky note on a text monitor saying what address to connect to, or something on a slide saying where to submit results. But when the adversary decommissions a given service, that configuration could remain, either because DNS records fail to get deprovisioned or a sticky note doesn't get shredded. Later, if an adversary allocates those IP addresses, and as we've shown, an adversary indeed can allocate those IP addresses, those clients will continue to connect and send sensitive data. We did a large-scale measurement study of how sensitive or how vulnerable a lot of Amazon services are to this, and what we found was that it was highly prevalent. We found a variety of cloud services that continued sending sensitive information to IP addresses even after a tenant sort of released that IP and it could be reused by an adversary. And we found a variety of other issues such as the domain name system. In aggregate, we found over 5,000 organizations that were vulnerable, and this was all enabled by DScope's Vantage Point. We disclosed these results to Amazon, and we actually have some empirical data that those disclosures led to dramatically decreased vulnerability on real-world deployed services to AWS. Just as an example to show the severity of this issue and the benefit of solving it, as a result of these misconfigurations on Amazon Web Services, any adversary could easily receive information on financial transactions, anything on a driver's license, real-time location history, and so on, simply by listening to traffic on public cloud IP addresses. In addition to these specific study outcomes, we also have some other data sets that are sort of useful for more general purpose, non-security internet measurement. We have raw PCAPs of sort of all of this scanning behavior, and we have application layer from this, as well as we can build synthetic darknet data sets if you're mostly just interested in those flow tuples. One limitation right now is that we're currently limited to TCP traffic, although we're working to resolve this. We also get information on sort of broad scanning events, same as conventional internet telescopes, although there are also some limitations here. So where does this leave us? And partially, I mean, for this work, and partially for just broad-scale internet measurement in general. Existing vantage points work on limited footprints, and they sort of deal with maximizing the quantity of traffic. The community in this space really needs to focus more on the quality of the traffic that we receive. I think DScope is a great first step toward that, but we need to think about how we can deploy in other settings. With that in mind, one of the reasons I'm here is that I'm really interested in talking with people about deploying interactive measurement techniques in a variety of networks. Really, public clouds are just a small fraction of overall internet phenomenon. And so if you're interested in both sort of deploying these vantage points within your network and the types of insights that we can give you that would be actionable for your deployments, definitely get in touch. With that, I want to thank you for your time, and I'm happy to take questions.
Jesus. Hi, everybody. My name is Blind. I'm Patrick from Meta, but I'm speaking for myself. Amazon obviously has more address space than anybody on the planet, I believe, but they're not the only cloud provider. If somebody watches this talk, maybe they stop targeting Amazon. Have you thought about it doesn't seem like it would be insanely difficult to automate this across lots of providers, big and small, and just randomize all over the planet?
Yeah, absolutely. From our standpoint, a future measurement goal is that we want to build apparatus that makes it really easy for network operators to sort of self-service deploy something like this. So one way that we can do that is sort of through like a VPN setup. We also have like a virtual machine appliance approach, where basically we can give you an ISO or a Docker image, and you can just put this in your network, and we can give you insights sort of in a self-service fashion.
All right, thanks.
Yep.
Hi, Ben, BGP Tools. Out of interest, you mentioned that Amazon was the most economical thing to do the IP harvesting, I guess, operation on. How bad were the other providers? Like, what are the billing like on other cloud providers or other large sources of IP addresses?
Yeah, so the key difference here, and unfortunately for my wallet, this is changing in the near future, is that Amazon effectively gives you public IP addresses when you buy compute. And so we basically go to Amazon and say, give us all your misfit instances, and we take the cheapest stuff there, and that makes it really cheap for us. The other providers charge for public IP addresses on a per hour basis. In February of next year, Amazon is actually going to start charging about the same amount. So in that way, the price competitiveness is really going to dissolve. It'll be about the same. That being said, there are still a lot of advantages to AWS. Big thing is the diversity of their IP address pool, right? So Amazon has something like as many IPv4s as the next two cloud providers combined. And the diversity of those in terms of things like /16s and /8s that they cover is just incredibly wider. For instance, DScope has collected data on, I believe, 34 /8s.
Cool. Out of interest, does that mean that we might see an interesting new version of your paper in the future around the difference between Azure scanning or Azure targeting or Google Cloud targeting and Amazon targeting? Because I feel like there will be a difference there. There will be people specifically searching out for Amazon IP addresses.
Yeah, in this case, the goal is actually even a little bit more broad than that, in that it's not just going to be the cloud providers. The next question that I'm in the process of answering is, what is the best vantage point in aggregate, right? So if we can have a little bit of footprint everywhere, what is it that we can see, and what sorts of questions can we answer for people?
Cool, that's really cool. Thanks.
Thanks. Okay, well, looks like no more questions. Thanks, everyone.